19 May 1957, Maralinga Test Site, South Australia, a remote stretch of desert chosen for Britain's atomic weapons program. At 10:32 in the morning, dosimeters along the perimeter begin registering readings, 25 millisieverts per hour. The Vixen B test, designed to simulate plutonium dispersal from a failing nuclear weapon, was meant to produce controlled fallout within predicted boundaries. Facility logs had anticipated modest increases in ambient radiation. Instead, instruments showed contamination spreading far beyond expected zones. Operators checked their equipment twice. The numbers held. Evacuation protocols, outlined for contained incidents, suddenly applied to areas thought secure. Workers in protective gear moved toward vehicles. Helicopters lifted off to survey the dispersion pattern. In the hours ahead, radiation monitors would detect plutonium particles in locations the models had deemed safe. From this reading began a chain of events that would force a reckoning with the true behavior of airborne radioactive materials and reshape nuclear testing policy across continents. The Maralinga Range sprawled across the traditional lands of the Anangu people, 300 kilometres northwest of Woomera. Britain selected the site in 1952 after losing access to testing grounds in the Pacific. The Australian government agreed. Prime Minister Robert Menzies saw strategic value in supporting Britain's nuclear deterrent. The arrangement formalised quickly. By 1953, surveyors were marking boundaries. By 1956, construction teams had erected observation towers, instrument bunkers, and temporary housing for hundreds of personnel. The British Atomic Energy Authority coordinated operations from Aldermaston. The Royal Australian Air Force provided logistical support, transport aircraft, perimeter security, meteorological data. Scientists from the Atomic Weapons Research Establishment arrived in rotations. Their mission? Test atomic devices and study the behavior of fissile materials under various conditions. Between October 1956 and October 1957, 7 major trials took place. Codenames followed the pattern of wildlife: buffalo, then antler. But alongside these full-yield tests, another program ran in parallel: Vixen B. The name appeared in classified documents with minimal explanation. Unlike the kiloton-range devices that produced mushroom clouds visible from Adelaide, Vixen B trials involved no nuclear detonation. Instead, they simulated weapon accidents, scenarios where conventional explosives might scatter plutonium without achieving criticality. The objective was specific: measure how far weapons-grade plutonium would travel if a bomber crashed or a warhead malfunctioned during handling. Defense planners needed data on dispersal patterns, contamination zones, and cleanup requirements. 4 Vixen B trials occurred between June and October 1957. Each test positioned a plutonium assembly atop a steel tower. Conventional high explosives surrounded the core. Detonation shattered the assembly, creating an aerosol cloud of plutonium particles. No chain reaction followed, only dispersal. Monitoring stations ringed each test site at intervals of 50, 100, and 200 meters. Additional stations extended outward to 500 meters. Wind gauges and weather balloons provided atmospheric data. The first Vixen B test proceeded on the 14th of June. Technicians positioned instruments according to meteorological forecasts. Winds were predicted to carry particles eastward, away from the main camp. Detonation occurred at dawn. Initial readings matched predictions. Activity concentrated within 100 meters. Perimeter monitors recorded levels described as manageable in subsequent reports. A health physics team surveyed the area on foot, collecting soil samples at marked intervals. Laboratory analysis confirmed plutonium-239 concentrations between 0.01 and 0.1 becquerels per gram, within anticipated ranges for the dispersal tonnage used. Planning for the second test began immediately. Engineers reviewed the first test's data, noting particle size distributions and deposition patterns. They adjusted monitor placement slightly, adding stations to the northeast quadrant. Meteorologists provided updated wind forecasts. Conventional explosive charges were recalibrated to produce a more uniform dispersal cloud. The test date was set for the 19th of May. On the morning of the 19th, personnel assembled at 0600 hours. a senior test director conducted the final safety briefing in the operations bunker. Dosimeters were distributed. Each technician clipped one to their collar. Perimeter guards received portable survey meters. Communications checks confirmed all stations were online. Meteorological data arrived at 0730. Winds from the west-southwest at 8 kilometers per hour, expected to hold steady through mid-morning. Forecasters saw no frontal systems approaching. Conditions were deemed suitable. At 0900 hours, the countdown sequence began. Personnel withdrew to designated safe positions. The test director's voice came through on radio channels. Vixen B2, stand by. At 0915, the conventional charge detonated. A brown-grey cloud rose above the tower, expanding laterally as it climbed. Within seconds, it reached 50 meters altitude. Winds began carrying it eastward, exactly as predicted. Monitoring stations transmitted data in real time. For the first 12 minutes, readings aligned with pre-test models. Dosimeters near ground zero registered elevated counts, expected given the proximity. Perimeter stations at 100 meters showed activity consistent with the first test. At 0927, a monitor 300 meters downwind recorded a sudden increase. Within 2 minutes, the reading climbed from background 0.1 microsieverts per hour to 2.5 microsieverts per hour, still within operational limits but higher than the model suggested. At 1032, dosimeters along the outer perimeter, 500 meters from the detonation point, began alarming. The readings were unmistakable, 25 millisieverts per hour. This figure exceeded evacuation thresholds by a factor of 10. A health physicist stationed at the eastern boundary checked his instrument twice, suspecting malfunction. The reading held. He radioed the operations bunker. Station 7, reporting 25 millirem per hour. Repeat, 25 millirem per hour. The voice was calm but insistent. Inside the bunker, the test director consulted contamination response protocols. Standard procedure called for immediate survey of affected areas and confirmation with secondary instruments. 2 mobile teams deployed in Land Rovers carrying portable scintillation counters. They reached the eastern perimeter within 8 minutes. Both confirmed the initial reading. One technician noted in his logbook, "Activity far exceeds predicted levels. Source unclear. Dispersion cloud should have passed overhead by now." The disparity was stark. Pre-test calculations based on the first Vixen B trial and theoretical models of particle behavior had predicted maximum concentrations within 200 meters. Beyond that distance, activity was expected to drop to near background. Instead, hotspots were appearing half a kilometer away, and readings suggested the plume was still mobile. By 10:45, the evacuation order was issued. Non-essential personnel were directed to withdraw from the test range to the main camp, 8 kilometers southwest. Essential monitoring staff remained, tasked with tracking the contamination front. A senior health physicist later wrote in his report, "The dispersion pattern observed on 19 May did not conform to any model in our reference set. Plutonium was detected at distances and concentrations incompatible with the charge weight and meteorological conditions." The Vixen B tests were designed around a specific premise. Conventional explosives could fragment a plutonium core into particles small enough to become airborne, but large enough to settle within a confined area. Weapons designers needed this data to evaluate the radiological consequences of accidents during transport or storage. If a transport aircraft crashed, or a warhead's chemical explosives detonated prematurely, how far would plutonium travel? How intense would the contamination be? How difficult would cleanup prove? To answer these questions, engineers at Aldermaston constructed test assemblies that mimicked operational warhead geometry. Each assembly contained between 1 and 2 kilograms of weapons-grade plutonium, primarily plutonium-239 with a small fraction of plutonium-240. Surrounding the core were shaped charges of conventional high explosive, arranged to maximize fragmentation without initiating a nuclear chain reaction. The assembly sat atop a steel tower, positioned to allow particle dispersal at roughly head height, simulating a surface-level accident. Instrumentation for the first Vixen B test reflected standard radiological survey practice of the mid-1950s. Film badges provided passive dosimetry for personnel. Ionization chambers, positioned at fixed intervals, measured real-time dose rates. Air samplers drew atmosphere through filter papers, capturing particles for later analysis. Soil sampling kits allowed collection of surface contamination at marked grid points. Meteorological towers recorded wind speed, direction, temperature, and humidity. The detonation itself lasted milliseconds. High explosive pressure waves shattered the plutonium, creating a dense aerosol. Particle sizes range from sub-micron fragments, small enough to remain suspended for hours, to larger chunks that fell within seconds. The mixture behaved as both a gas and a particulate cloud. Initial expansion was rapid, driven by explosive force. Once the pressure wave dissipated, atmospheric physics took over. Wind carried the finer particles downwind. Larger fragments settled near the tower. The boundary between the two regimes was not sharp. It depended on particle mass, air turbulence, and local topography. During the first test in June, most activity stayed within the predicted zone. Post-test surveys found plutonium concentrations highest near ground zero, declining exponentially with distance. At 50 meters, samples showed 0.5 becquerels per gram. At 100 meters, 0.1 becquerels per gram. Beyond 200 meters, concentrations approached background variability, detectable but low. The test was declared a success. Data matched models closely enough to inform design decisions. The second test, the 19th of May, used a similar assembly but with refined instrumentation. Additional air samplers were deployed at 300 and 500 meters. More soil sampling stations were added to capture deposition gradients. Meteorological forecasting was reviewed in greater detail to avoid unexpected wind shifts. Everything pointed toward a repeat of June's controlled dispersal. The detonation occurred at 9:15 as scheduled. Observers in the bunker watched through periscopes and remote cameras. The explosive cloud rose cleanly, without visible irregularities. Initial expansion looked identical to the first test. Winds carried the cloud eastward at the expected velocity. For the first 10 minutes, transmitted data confirmed predictions. Then the numbers began to diverge. Air samplers 300 meters downwind registered activity levels 3 times higher than the June test, despite using a comparable charge. By 9:30, dosimeters at 400 meters were showing readings that should have appeared only at 100 meters. Something was carrying plutonium farther and faster than the model allowed. At 10:32, the outer perimeter alarms triggered. 25 millisieverts per hour, a reading impossible under the dispersal assumptions used during planning. A millisievert is 1,000th of a sievert, the SI unit of ionizing radiation dose. 25 millisieverts per hour represented a dose rate sufficient to reach annual occupational limits in 40 hours of exposure. For comparison, natural background radiation in most environments delivers roughly 0.003 millisieverts per hour. This was 8,000 times higher. Mobile survey teams confirmed the reading within minutes. Scintillation counters, instruments that detect gamma radiation by measuring light flashes in a crystal, showed consistent results across multiple instruments. The contamination was real, not an instrument fault. Further complicating the picture, the activity was not uniformly distributed. Hotspots appeared in seemingly random locations, separated by areas of much lower activity. This patchiness suggested that particle deposition was being influenced by local wind eddies, terrain features, or thermal currents, variables not captured in the pre-test models. A health physicist collected air filter samples from the eastern perimeter at 1100 hours. Laboratory analysis later revealed plutonium-239 concentrations of 1.2 becquerels per cubic meter of air, far above the permissible exposure limit for uncontrolled areas. Particle size analysis showed a bimodal distribution. Most particles were either submicron or between 10 and 50 microns. The submicron fraction remained airborne longest, carried by convection and diffusion. The larger particles settled within hours, but unpredictably. By noon, perimeter monitors had mapped a contamination plume extending over 1 kilometer from the detonation point. The plume was asymmetric, broader to the northeast than to the direct east. This suggested wind direction had shifted slightly during the critical first hour after detonation. a shift too subtle to be captured by the meteorological instruments, but sufficient to move particles off the predicted track. The test director convened an emergency meeting at 1300 hours. Present were the senior health physicist, the meteorological officer, the test engineer, and representatives from the Australian Department of Supply. The health physicist presented the data without editorializing. Contamination has been detected at distances exceeding model predictions by a factor of 5. Dose rates at the outer perimeter exceed evacuation thresholds. Air sampling indicates respirable plutonium particles at concentrations above permissible limits. Recommendation: suspend further Vixen B tests until dispersal models can be revised. The meteorological officer reviewed wind data. Nothing in the atmospheric record explained the anomaly. Winds had been steady within the forecast range. No frontal passages, no unexpected gusts. The test engineer examined the explosive assembly records. Charge weights matched specifications. Detonation timing was precise. No equipment failures were recorded. The conclusion was unavoidable. The models themselves were flawed. They had underestimated how far fine plutonium particles could travel under even modest wind conditions. They had failed to account for the persistence of submicron aerosols. They had not considered the role of turbulence in creating localized hotspots far from the main plume axis. At 1400 hours, evacuation orders were extended. All personnel not involved in contamination monitoring were withdrawn to the main camp. The test range was declared a controlled area. Entry required full protective equipment and dosimetry. A decontamination station was established at the perimeter. Personnel exiting the range were surveyed with handheld monitors and directed to shower if contamination was detected. One technician, writing in his personal journal that evening, summarized the day. "We thought we understood how plutonium would behave. The instruments say otherwise. Now we clean up and figure out what we missed." The immediate response to the 25 millisievert per hour readings focused on personnel safety and contamination mapping. By mid-afternoon on the 19th of May, all non-essential workers had been relocated to the main camp. Essential staff, health physicists, survey technicians and security personnel remained under strict protective protocols. Each wore full coveralls, respirators, and carried personal dosimeters checked hourly. Survey teams divided the test range into a grid. Each square measured 50 meters on a side. Teams moved systematically through the grid, taking readings at the center of each square and at the corners. The process was slow. Instruments required time to stabilize. Sample collection added further delays. By nightfall, teams had surveyed only the eastern quarter of the range, the area directly downwind of the detonation point. Preliminary maps showed contamination concentrated in a wedge-shaped zone extending northeast from the tower. The highest activity remained near ground zero, but secondary hotspots appeared at 200, 400, and 700 meters. These hotspots were small, typically 5 to 10 meters in diameter, but intense. One sample collected at 420 meters registered 11 millisieverts per hour at ground level. Soil collected from the same location showed plutonium concentrations of 3.7 becquerels per gram. By the evening of the 20th of May, survey teams had covered 80% of the predicted contamination zone. The map was troubling. Activity extended farther east than any model had suggested. Trace amounts of plutonium were detected at 1.5 kilometers, 3 times the maximum distance considered plausible during planning. Air samples collected at this distance showed plutonium-239 at concentrations just above detection limits, but definitively present. An internal memorandum dated the 21st of May, authored by the senior health physicist, summarized the findings. Survey results indicate widespread dispersal of plutonium aerosol beyond predicted boundaries. Contamination persists at measurable levels to distances of 1.5 kilometers from the test point. Dose rates at selected hotspots exceed 1 millisievert per hour. Air sampling confirms respirable fraction remains suspended. Recommend full-range survey to establish true extent of affected area. That recommendation was approved. Over the following week, teams expanded the survey grid, covering a circular area with a radius of 3 kilometers. Most of this area showed background-level activity, but isolated hotspots continued to appear in unexpected locations. One was found 900 meters south-southwest of the tower, upwind of the detonation point. The only plausible explanation was that a small eddy, undetected by surface weather instruments, had carried particles against the prevailing wind during the critical first minutes after detonation. Particle size analysis provided additional insight. Samples collected at various distances were shipped to Aldermaston for detailed laboratory examination. Electron microscopy revealed that the smallest particles, those below 1 micron in diameter, accounted for less than 10% of the total plutonium mass, but dominated the respirable fraction. These particles could penetrate deep into lung tissue if inhaled. They remained airborne for hours, subject to diffusion and convection. Their behavior was less predictable than that of larger particles, which followed ballistic trajectories and settled quickly. The bimodal distribution, submicron and 10 to 50 micron particles, had not been anticipated. Pre-test models assumed a continuous size spectrum, peaking around 5 microns. In reality, the explosive fragmentation process created two distinct populations. The submicron particles formed from vaporized plutonium that condensed in the cooling fireball. The larger particles were mechanical fragments of the original core, shattered but not vaporized. Each population dispersed according to different physics. By the end of May, the contamination survey was complete. The affected area covered approximately 4 square kilometers, though contamination levels varied by orders of magnitude. High-activity zones, defined as areas exceeding 1 millisievert per hour, covered roughly 0.15 square kilometers. Medium activity zones, between 0.1 and 1 millisievert per hour, added another 0.6 square kilometers. Low activity zones, above background but below 0.1 millisievert per hour, accounted for the remainder. Cleanup. Planning began immediately. The challenge was daunting. Plutonium-239 has a half-life of 24,100 years. Contamination would not decay to negligible levels on any human timescale. The only option was physical removal. Scrape contaminated soil, dispose of it properly, and verify that residual activity met acceptable limits. Initial cleanup efforts focused on the highest activity zones. Crews used scrapers to remove the top 5 centimeters of soil, loading it into steel drums for disposal. Each drum held approximately 0.2 cubic meters and weighed 250 kilograms when full. After filling, drums were sealed, labeled with activity content, and transported to a designated storage area. Post-scraping surveys checked whether activity had been reduced to acceptable levels. If not, another layer of soil was removed. The process was labor-intensive and slow. Crews could clear roughly 50 square meters per day under optimal conditions. High activity zones, where dose rates limited working time, took longer. Workers rotated frequently to avoid exceeding dose limits. Personal dosimeters were checked after each shift. Cumulative doses were tracked in individual logbooks. By mid-July, crews had cleared approximately 0.05 square kilometers, 1/3 of the high activity zone. 800 steel drums sat in temporary storage. Each drum contained an average of 1.5 megabecquerels of plutonium-239. Total inventory, 1.2 gigabecquerels, enough activity to make disposal a long-term concern. Waste disposal options were limited. Burial on site was the default choice, but required careful site selection. The burial ground needed to be geologically stable, remote from groundwater, and accessible for monitoring. Engineers selected a location 5 kilometers west of the test range. Trenches were excavated to a depth of 3 meters. Drums were stacked in layers separated by fill. After each trench was full, a clay cap was applied to limit water infiltration. Markers were placed indicating the nature of the buried material. Meanwhile, contamination at medium and low levels remained largely unaddressed. Resources were insufficient to clear the entire 4 square kilometers. A decision was made to focus on areas with potential for future use, and to post warnings around zones deemed too contaminated for unrestricted access. This decision reflected a broader challenge: defining acceptable residual contamination. No consensus existed on safe plutonium levels for land that might eventually be released for other purposes. Regulatory frameworks in the 1950s were rudimentary. Dose limits existed for workers, but environmental standards were vague. The Maralinga site, owned by the Australian government, but operated by Britain, occupied a legal grey zone. Australian authorities deferred to British radiation protection guidance, which was itself evolving. An internal debate emerged. Some health physicists argued for aggressive cleanup, removing contamination to the lowest achievable levels. Others advocated a risk-based approach, prioritizing areas where human exposure was most likely. Cost and time were factors. The Vixen B program included 4 tests. 2 remained to be conducted. Delaying them indefinitely would jeopardize the entire research effort. In August, a compromise was reached. Cleanup of high-activity zones would continue. Medium-activity zones would be surveyed and posted with warning signs. Low-activity zones would be monitored periodically but otherwise left undisturbed. The remaining 2 Vixen B tests would proceed, but with revised procedures, larger exclusion zones, more extensive monitoring, and contingency plans for unexpected dispersal. On the 14th of September, the 3rd Vixen B test was conducted. Contamination again exceeded predictions, though not as severely as in May. The 4th test, on the 9th of October, produced similar results. By the end of October, the Vixen B program was complete. The data collected would inform weapon safety assessments for years. But the contamination remained, a legacy that would outlast the program, the facility, and many of the people who created it.